All right, this video is about chapter 7. We are going to do some problems and we're going to talk about the general equations for this chapter. So let's start with a problem and then we're going to talk about how we can solve that problem. So first, let me just put some equations on the screen that are going to be important for this chapter. Okay. And we're going to be working on applying these to different problems, but let's review a little bit. Okay. So for centripetal acceleration, we saw that centripetal acceleration is equal to v squared over r. Right. And you can always put that acceleration into Newton's second law. So you could have the centripetal acceleration equals m times ac, which is the centripetal acceleration, and we can substitute that with our expression. So v squared over r. Okay. Um, we also saw that we can find the velocity um, by taking basically the circumference of a circle, 2 pi r, and dividing it by t, the time it takes to go around a circle. Okay. And frequency is the number of times something happens in a second. For example, the number of rotations of your motor, the rotations of a wheel in 1 second, or maybe even it's something like waves passing you on the ocean. Maybe you're sitting on the beach and you count the number of waves, um, and you say, all right, how long does it take for a wave to crash on the beach? That would be the period. And if you know the period, so uh, you can find the frequency, right? So 1 over t is equal to the frequency, okay? And we're also going to talk about some important things this chapter called one of those is arc length, okay? And so the one that you're most familiar with, let's say we started here and we start moving in some type of circular motion, okay? And we end up back where we started, okay? Well, if you go all the way around a circle, okay, then the angle that you would travel, okay, so as you start moving here and eventually go all the way around the circle, well, you would travel 360 degrees. Okay. That's the angle that you would go around the whole circle. Okay. This would be the angle that you cross, or in radians, okay, that would be 2 pi. These are both different ways that we can express an angle. Okay. And but for this chapter, we're going to start expressing things in radians. Okay. If you go halfway around a circle, okay, so this would be half of a circle. Okay. That would be pi radians. This is half a circle, or it, um, or 180 degrees. Okay. So those are the kind of the same ways. Other measurements, okay, so pi over 2, that's going to equal 90 degrees. Okay, so this is kind of our reference point here. We could go maybe so 90 degrees would be here. Okay, that is a quarter of a circle. Okay, and our angle here is 90 degrees. Okay, so if we went like this, okay, our angle is 90 degrees. Okay, so these are important ways that we're gonna keep track of our circle. Okay, so let's draw a little diagram here and we'll make another circle and we'll kind of make a angles. Okay, I like to make pictures. Okay, so up at the top here, this would be 0 degrees or 0 radians. Okay, if we went over here, Okay, this was 90 degrees, um, or um, pi over 2 radians. Okay, if we went down here, this would be 180 degrees, or it would be pi radians. Okay, or if we went over here, this is 270 degrees. And so that if we go this way, that's pi over 2, then pi here, so we'd add another pi over 2. Okay, and so this would be um 3 halves pi. Okay, that would be our angle right here. And we could get that. We could say, okay, 270 degrees would basically be the same as going 90 plus 90 plus another 90 degrees, right? To get to 270 degrees. So we go one, two, three. Or if we did it in radians, this would be 3 pi over 2. And we get that because 90 degrees is pi over 2 plus pi over 2 plus pi over 2. Okay? So if you add 1 half plus 1 half plus 1 half, that gives you 3 halves. And then we have a pi there, so that's how we get 3 pi over 2. Right? And then if we went all the way back around, that would give us 4 pi over 2, or we would have 2 pi. So right there. Okay? So these are our angles in radians. Okay, so let me write that down. This is angles in radians or rads, right? Because physics is rad. Hmm. Wow. Okay, that was even. I thought that was corny, but oh well, that's what happens. So let's look at an example of a problem here. So this is problem 7.11. Um, so what do we have here? Okay, so the 5.5 centimeter long second hand on a watch rotates smoothly. Okay, so that's important because that means we have a constant angular velocity, right? That's like if something's spinning. The speed that it spins at doesn't change. Okay, so what is its angular speed? Okay, and then what is the speed of the tip of the hand? Okay, so we need to talk about, first of all, um, when we say angular speed, what does that mean? Because we know what normal speed is. That's how fast the distance is changing. Okay. But angular speed would be basically the rate that the angle is changing. Okay. So it doesn't have units of meters per second, but it could be radians per second. Okay. So let's look at the PowerPoint slide for that. And there's some very useful equations in the PowerPoint, and that is uploaded on Canvas. Okay. And so we're going to talk about a little bit about some of that right now. Okay. So let's talk about um, angular displacement. I think what this problem is asking for is they're basically asking us how many degrees in radi or how many radians per second is the hand going to change? Okay. Okay. So I actually found a clock, um, and I think my family won this for me at a fair, maybe one of those vending machines that costs $1. Okay, but let's look at an example of the second hand here. Okay, so one thing we can say about the second hand is we have the time because we know that this thing is going to move around the entire circle Okay. So in this clock, okay, the second hand travels around it once in every minute. And 1 minute has 60 seconds, okay? So if we wanted to get its angular speed or angular velocity, um, we can do that. Okay. So let's write down some information here, okay? And and we can think about this as, so this is angular speed. Okay, I put that wrong in my notes. Okay, so we're going to call angular speed or angular velocity is going to be omega, okay? And this is going to be the change in our angle theta divided by the time, okay? And this doesn't have to be for a complete circle, but it could be, okay? So here, let's write this out explicitly. So we'll have our final angle minus our initial angle divided by our final time minus our initial time. Okay, and I'm just writing everything out here in all of its glory. Sometimes we don't have to necessarily do that. Okay, so its initial angle, we'll call that 0, and its final angle is going to be 2 pi. Okay, so it'll be 2 pi minus 0. And um and the final time will be 60 seconds, and our initial time will be 0. Okay, so we've got our angle up here, and then down here in the bottom, that's our time. So we can put this in MATLAB, okay? And if we go over to MATLAB, we say 2 pi divided by 60, which gives us 0.1047. Okay, so let me write that down. Okay. So this gives us an angular speed 1047, and this will be radians per second. Right now, it's a little bit different than normal velocity because we don't have meters in this. Okay, that's okay. Right, and we want to keep track of degrees and radians, so that we can convert back and forth. Okay, but um. Yeah, so we're just gonna keep that in mind, basically. Okay. Okay. So let's draw a picture of our little pocket watch here. Okay, here's the second hand, and here's our clock. And our second hand is moving this way. Okay. It goes, we say that this is clockwise. Okay, and hopefully you know what clockwise means. I don't know if you kids nowadays have actually used uh clocks with hands on it. Probably you have. I don't know. Somebody said like kids nowadays don't know how to tell time with clocks with hands. Hopefully that's not true. I know everything has digital clocks on it now, but it's still important. Okay, so that basically is going to give us here, and then we'll call this 0.105 radians per second. Okay, omega. And I don't know if radians, if I would really consider it a unit like meters or kilograms, because really the angular frequency or the angular velocity, it's just 1/2 second. So you could think of this almost like hertz, 105 hertz, right? Because hertz, 1 hertz is equivalent to 1/2 seconds. Okay. All right. So here's my second hand. You can see it in my little clock right here. Okay. Now, yes, is it ticking? Yes. Some second hands are smooth. Okay. Some of them tick from, little tick mark to tick mark, right? But we can get its average velocity, right? Because we know basically where it was when it started and where it ended up. So that's its average velocity. We don't care about all the little jerks and twitches it had along the way. All right, so the second part of this problem, okay, it says, what is the speed at the tip of the hand? What is the speed at the tip of the hand? So we're talking, okay. So now here's our second hand, right? I drew this close-up picture of my second hand. I made it kind of kind of pointy here. Okay. I'm gonna color this blue. I used to have a watch when I was younger that would glow and the second hand would glow in the dark and it had a little glow in the dark tick marks on the thing. It was really cool. They put a little bit of maybe just a little bit of this radioactive stuff that glows in the dark. Maybe it charges up. Okay. Well, anyways, so the question is, what is our velocity right here on the tip of this thing? Okay. And when they say velocity, they mean, all right, what if there wasn't maybe like a little, I don't know what kind of creature. Oh, let's put a bed bug. Bed bug. Oh, here's our little bed bug. I know people think bed bugs are so gross. And they pretty much are gross. Let's maybe okay, well let's say it's an ant. Yeah, I don't know why I said that. Okay. So here's our ant on the end of our second hand. Okay. And let's say our ant is intelligent somehow and he can measure velocity. Okay. Now, yes, he's going in a circle, but he does have an instantaneous velocity this way. This is the tangential velocity, and it does have units of meters per second. Okay, so if there's a little insect riding on the end of that hand, okay, um, how fast would he measure? Okay, and we can also think about this in terms of let's say we have a car here. Okay, now if I drive my car in a circle, okay, and you can do this on a racetrack, maybe. Okay, my car is going in a circle here. Okay, well it's going to travel a certain distance that I could measure with the odometer. Okay. And that's basically going to be the distance it traveled around the circle, okay, divided by time, right? And that's in meters, okay? And so if this thing goes all the way around the circle, okay? So for one complete loop around the circle, that's a circumference. The circumference of my circle. Okay, and what is the formula for circumference of a circle? Well, in math and physics, we call it something else. It has another name. It's called the arc length. Okay, and so this is my arc length. Okay, arc length. Okay, we'll call it S. Right? And arc length is defined as the radius of the circle divided by um, the angle. Okay, and that's basically if my ant here on the end of the second hand could measure meters, how far did he move around? Right? Because here's our second hand, right? This thing, right? There's a certain radius, and so every second, the distance that it travels is one circumference of the circle here. Okay. And let's calculate it here for my watch face. Okay, I'm gonna do it in centimeters. Okay, so where's the end of this hand? It goes almost to the edge of the number. Okay, so we'll measure from the edge of the nine here. Is that right? About to the edge of the three to the yeah, so from the nine to three. Okay. So where does it go? All right, so here's my Okay, so from the edge of the nine until the edge of the three, I'm gonna say it is really 1.3 centimeters. Okay. So let's do it for my little watch here. Okay. I'm not gonna do it for the homework problem, but I have a watch here, so let's do it for this. I want to find out what is my velocity of this thing, okay, of my watch here in meters per second. Okay, so here's my watch. Put this little pocket watch up here. I don't know what people have like clocks anymore. I don't have a watch. I mean, I have an Apple Watch, but I can make a digital hand appear on it, which actually I do when I wear my Apple Watch. Usually I just forget. Okay. So the circumference of my circle, okay, so We'll call this C is equal to 2 pi times r, the radius of my circle. Okay, and I measured that the diameter, right? So diameter is equal to 2 times the radius, right? So we can call this D equals 2 times r. Or if I know the diameter, then the radius, of course, is equal to the diameter divided by 2. Okay, so my diameter was, okay, so my diameter was 1.3 centimeters. I want to convert that into meters. So that's going to be 0.013 meters. Okay, wonderful. So now I'm going to find my radius. Okay, so that's going to be 0.0132. And I like to leave the zero here, just like, if you're in the medical profession, because then you see 0.013. I don't accidentally misread this and not see the decimal place there. Okay, so that's kind of important. Okay, so there's one. All right, so let's go throw this in MATLAB. So it should be, I think, 0.0065. Okay, so what does MATLAB say? MATLAB. Okay, so 0.013 divided by 2, it's 0.0065. All right, there we go. Okay, we got that. Okay, so my radius is 0.0065 meters. Wonderful. Stop my sharing here. Okay, so then I'm going to calculate the circumference of so here's my watch. Okay, so the circumference of this thing is going to be 2 pi times 0.0065 meters. Okay, that's going to be my circumference. Go back to MATLAB here. Okay, so that is going to be uh, 2 times pi times 0.0065. All right. So the circumference of the circle that the end of this thing travels on, I'm gonna write it down here. It's gonna be 0.0408. Okay, that's enough decimal. That's gonna be, and I'm gonna round it off there to 1. I don't need any more. Okay, so here's my circumference. Okay. And remember, this is also, I could also call this the arc length. I could call it S because the formula for that is 2, yeah, it's going to be the radius times the angle. Okay. Radius times the angle. Let me rewrite that here. So arc length. Okay. So arc length, we call it S, and it's going to be R times theta, the distance that you traveled, or the angle, right? So in this case, we went all the way around the circle. We went 2 pi, okay, which is a circumference. So circumference is a special case of arc length, okay? And now we need to get our velocity, okay? And I think we mentioned this in the last chapter. I definitely I maybe said this, okay? Um But our velocity here is going to basically be s divided by t. Okay, so velocity, object in circular motion. Right. So now we're just going to plug in the numbers here. Okay, well, what do we need to put? Well, okay, the distance that we traveled was 2 pi r here. Okay, and we know what the period is, right? Our period is how long does it take the hand to move around our watch? Okay, well, that's 60 seconds. Okay, so here's what we know. Okay, so the period equals 60 seconds because it's 1 minute. And the distance that it traveled, S, the arc length. Okay, in this case, it is 2 pi r, and that is one complete circle. Okay, so we've got 2 pi r there. So now we can plug in all of our numbers. Okay, so this really becomes c over t. We already calculated c up here, so I'm just going to put that in up there. Okay, so that's going to be 0.0400841 meters divided by 60 seconds. Okay, and this is going to be our velocity in meters per second. So we've got meters here and seconds. So we know that our units are in meters per second. Okay, and let's compare that to angular velocity for a second. Over here, when we calculated omega, which is our angular velocity, we got radians per second. We did not have meters in there. Okay, so that's kind of a key difference, right? The units. All right, so I'm gonna put this into MATLAB now, and we'll see what we get for our velocity. Okay. All right. So we have our, oh yeah, it's right there. The number is 0.0408 407, and I'll just leave the extra digits in there while I'm doing the calculation. When I'm done, then I'll round it off. Okay, and this is divided by 60. Okay. So all right. So then that gives us a velocity of 6.806784 times 10 to the minus 4 meters per second. All right. So there's our answer. We're gonna round that off. Okay. So this is gonna be, we'll say that this is 6.81 times 10 to the minus 4 meters per second. Okay, so our units check out. We're in meters per second, and so that looks like it. Okay, so I did this in meters per second. Okay, I think that in the problem, it's going to ask, it wants you to do it in centimeters per second. Okay, so if you want to do this in centimeters per second, then you'd have to say, okay, well, I know that 100 centimeters equal 1 meter. So you're going to basically multiply your answer by 100 centimeters per second. That's going to cause your meters to cancel, and then your answer is going to be in centimeters per second. Okay, so make sure you check out the units that you're supposed to enter the answer in, and so you don't mess that up, basically. Okay, so this covers basically section 6.1, or no, this covers section 7.1 of the book, and we also solved a problem. Okay, so and I like using specific problems to go through the material. So hopefully this saves you time, and we get to the point a little bit quicker. So thanks for watching this video, and I will be posting lots more videos about chapter 7, and then probably one more about chapter 6, orbital motion. Thanks for watching.
Thank you. Like and subscribe down below.